When certifying enclosures for plenum spaces, a definitive resource is UL 2043, the standard for safety for plenum cable and equipment. Additionally, consider ASTM 84, the standard test method for surface burning characteristics of building materials, and NFPA 90. A, the standard for the installation of air conditioning and ventilating systems. Regarding low voltage differences in requirements between walls and ceilings, there are some key distinctions. For walls, the cable must be secured every 2 feet. Cable can be run within wall cavities as long as it is protected from damage. Enclosures may need to be fire-rated if located in a fire-rated wall. For ceilings, cable must be run in cable trays or raceways. Cable must be secured at regular intervals. Enclosures must be plenum-rated if located in an air handling space. New York City and Chicago have unique and strict low-voltage requirements. The New York City Electrical Code is found in Chapter 36 of the Code of the City of New York. The Chicago Electrical Code is in Chapter 13 of the Municipal Code of Chicago. These codes may have specific requirements for low-voltage cabling. In New York City, cables must be under ITER's laboratories listed and tested in accordance with UL 2043. In Chicago, cables must be installed in accordance with ANSI/TIA/EIA-568. C2. Both cities may require inspections for low-voltage installations. Several resources can help validate specific requirements. Firstly, the National Electrical Code, specifically Article 800, provides guidance. Secondly, BICSI low-voltage cabling standards can be found at the BICSI.org website. Thirdly, TIA standards for telecommunications cabling are available at TIAonline.org. Fourthly, Underwriters Laboratories et al.com provides information on plenum-rated cables. Fifthly, the National Fire Protection Association has resources at NFPA.org. Let's delve deeper into each of these areas. UL 2043 is crucial for ensuring that materials used in plenum spaces, which are air handling spaces above ceilings or below floors, meet stringent fire safety standards. This standard evaluates the fire and smoke characteristics of products intended for installation in plenums. Products that meet UL 2043 requirements are designed to limit the spread of fire and smoke, providing valuable time for evacuation and minimizing damage. ASTM 84 is another important standard for assessing the surface burning characteristics of building materials. This test method measures how quickly a flame spreads across the surface of a material and the amount of smoke it generates. The results of ASTM 84 testing are used to classify materials based on the flame spread index and smoke developed index, which are important factors in building codes and fire safety regulations. NFPA 90 provides comprehensive requirements for the installation of air conditioning and ventilating systems to prevent the spread of fire and smoke. This standard covers a wide range of topics, including duct construction, fire dampers, smoke detectors, and control systems. Compliance with NFPA 90 helps to ensure that air handling systems are designed and installed in a way that minimizes the risk of fire and smoke spreading throughout a building. When it comes to the differences between wall and ceiling installations, the key considerations are cable support, protection, and fire rating. In walls, securing the cable every 2 feet helps to prevent it from sagging or becoming damaged. Running the cable within wall cavities provides a degree of protection from physical damage, but it is important to ensure that the cable is not exposed to sharp edges or other potential hazards. If the wall is fire-rated, any enclosures located within the wall must also be fire-rated to maintain the integrity of the fire barrier. In ceilings, cable trays or raceways are typically required to provide support and protection for the cable. Cable must be secured at regular intervals to prevent it from sagging or becoming tangled. If the ceiling space is used as an air handling plenum, any enclosures located in that space must be plenum rated to prevent them from contributing to the spread of fire and smoke. New York City and Chicago have some of the most stringent electrical codes in the United States. These codes reflect the unique challenges and risks associated with densely populated urban environments. The New York City Electrical Code and the Chicago Electrical Code both incorporate the National Electrical Code, but they also include additional requirements that are specific to their local conditions. In New York City, the requirement for cables to be under IT's laboratories listed and tested in accordance with UL 2043 reflects the city's focus on fire safety in plenum spaces. In Chicago, the requirement for cables to be installed in accordance with ANSI/GA/EIA-568 C2 ensures that cabling systems are designed and installed to meet industry best practices for performance and reliability. Both cities may require inspections for low-voltage installations to verify compliance with their electrical codes. The National Electrical Code, or NEC, is a widely adopted standard for electrical installations in the United States. Article 800 of the NEC covers communication circuits, including low-voltage cabling. This article provides requirements for cable types, installation methods, grounding, and bonding to ensure the safety and performance of communication systems. BICSI, formerly known as Building Industry Consulting Service International, is a professional association that provides training, certification, and standards for the information and communications technology, or ICT, industry. BICSI's low-voltage cabling standards cover a wide range of topics, including cable selection, installation practices, testing, and documentation. These standards are widely recognized and respected in the industry and can be a valuable resource for anyone involved in the design or installation of low-voltage cabling systems. The Telecommunications Industry Association, or TIA, is another organization that develops standards for telecommunications cabling. TIA standards cover a wide range of topics, including cable performance, connector specifications, installation methods, and testing procedures. These standards are widely used in the industry and can help to ensure that cabling systems meet the performance requirements of modern telecommunications networks. Under IT's Laboratories, or UL, is a global safety certification company that tests and certifies products to ensure that they meet applicable safety standards. UL offers a variety of certifications for cables and enclosures used in low-voltage cabling systems, including certifications for plenum-rated products. UL certifications are widely recognized and respected in the industry and can provide assurance that products have been tested and meet rigorous safety standards. The National Fire Protection Association, or NFPA, is a non-profit organization that develops codes and standards for fire prevention and safety. NFPA standards are widely used in the United States and around the world and cover a wide range of topics, including electrical safety, fire protection systems, and building construction. NFPA 70, the National Electrical Code, is a key standard for electrical installations. When working with low-voltage systems, it is always important to consult the latest edition of the NEC and any applicable local codes to ensure that your installations meet all applicable requirements. Furthermore, always refer to manufacturer's specifications for proper use, installation, and ratings of low-voltage products. Always ensure you follow proper safety protocols, including but not limited to lockout, tagout, and personal protective equipment, or PPE. When dealing with electricity, always have a healthy respect. Failure to do so can lead to dangerous or deadly consequences. Always be aware of the dangers associated with electricity and take all necessary precautions to protect yourself and others. Consider the following example involving calculating voltage drop for low-voltage landscape lighting. You're installing a 12 volts landscape lighting system and need to determine the appropriate wire gauge to use for the main run from the transformer to the furthest light fixture. The total length of the wire run is 150 feet and the total load is 100 watts. Firstly, calculate the total current. Use the formula current equals power divided by voltage. So, current equals 100 watts divided by 12 volts, which equals 8.33 amps. Secondly, determine the maximum acceptable voltage drop. A general guideline is to limit voltage drop to no more than 5% of the source voltage. So, 5% of 12 volts is 0.6 volts. Thirdly, use a voltage drop calculator or formula to determine the required wire gauge. The voltage drop formula is voltage drop equals 2 times K times current times length divided by circular mils, where K is the constant for the wire material, approximately 10.4 ohm circular mils per foot for copper. Length is the length of the wire run in feet, and circular mils is the cross-sectional area of the wire. Rearranging the formula to solve for circular mils, we get circular mils equals 2 times K times current times length divided by voltage drop. Plugging in the values, we get circular mils equals 2 times 10.4 times 8.33 times 150 divided by 0.6, which equals 43,290 circular mils. Fourthly, select the appropriate wire gauge based on the calculated circular mils. Refer to a wire gauge chart to find a wire gauge that corresponds to the calculated circular mils. In this case, a 6 American wire gauge, or AUG, wire has a circular mil area of 26,240, which is not sufficient. A 4 American wire gauge, or AUG, wire has a circular mil area of 41,740, which is also not quite sufficient. A 2 American wire gauge, or AUG, wire has a circular mil area of 66,360, which is sufficient. Therefore, you would need to use a 2 American wire gauge, or AUG, wire for the main run to keep the voltage drop within acceptable limits. This example highlights the importance of considering voltage drop when designing low voltage systems. Using the correct wire gauge can help to ensure that the system operates efficiently and reliably. Note that these calculations are simplified and do not account for factors such as temperature and bundling of wires, which can affect voltage drop. It is always best to consult with a qualified electrician or electrical engineer to ensure that your low voltage systems are designed and installed correctly. Another example involves selecting the right type of cable for a specific low voltage application. You are installing a low voltage lighting system in a garden and need to choose the appropriate type of cable to use for connecting the light fixtures to the transformer. The cable will be buried underground and exposed to the elements, so it needs to be durable and resistant to moisture, sunlight, and other environmental factors. Firstly, consider the environmental conditions. The cable will be buried underground, so it needs to be rated for direct burial. It will also be exposed to moisture, sunlight, and temperature extremes, so it needs to be resistant to these elements. Secondly, determine the voltage and current requirements. The lighting system operates at 12 volts, and the total current draw is 5 amps. The cable needs to be able to safely handle these voltage and current levels. Thirdly, choose a cable type that meets the requirements. Common types of cable used for low voltage lighting systems include underground low energy circuit cable, or USE, and low voltage landscape lighting cable, or LLL. Underground low energy circuit cable, or USE, is a type of cable that is specifically designed for direct burial applications. It has a tough, moisture-resistant insulation that protects the conductors from corrosion and damage. Low-voltage landscape lighting cable, or LLL, is another type of cable that is commonly used for low-voltage lighting systems. It is similar to underground low-energy circuit cable, or USE, but it is typically smaller in size and less expensive. Fourthly, select the appropriate wire gauge. The wire gauge needs to be sufficient to carry the required current without excessive voltage drop. Refer to a wire gauge chart to determine the appropriate wire gauge for the length of the cable run and the amount of current it will be carrying. Fifthly, install the cable properly. Follow the manufacturer's instructions for installing the cable. Make sure to bury the cable at the recommended depth and to protect it from sharp objects and other potential hazards. In this example, underground low-energy circuit cable, or USE, would be a good choice for the low-voltage lighting system. It is rated for direct burial, resistant to moisture and sunlight, and available in a variety of wire gauges to meet the current requirements of the system. By choosing the right type of cable and installing it properly, you can ensure that your low-voltage lighting system operates safely and reliably for many years to come. When working with electrical systems, including low-voltage systems, it's critical to understand and adhere to local electrical codes and regulations. These codes are in place to ensure safety and prevent electrical hazards. They cover various aspects of electrical installations, including wiring methods, grounding, overcurrent protection, and equipment specifications. To comply with local electrical codes, firstly, familiarize yourself with the specific codes and regulations applicable to your area. These codes may vary from one jurisdiction to another, so it's important to consult the latest version of the code adopted by your local authorities. Secondly, obtain the necessary permits and approvals before starting any electrical work. Many jurisdictions require permits for electrical installations to ensure that the work is performed in accordance with the code. Thirdly, use only approved electrical materials and equipment. Ensure that all electrical materials and equipment you use are listed or labeled by a recognized testing laboratory, such as Underwriters Laboratories, or OL, or ETL, to indicate that they meet applicable safety standards. Fourthly, follow proper wiring methods and techniques. Install all wiring in accordance with the requirements of the electrical code. Pay attention to factors such as wire size, insulation type, conduit fill, and support methods. Fifthly, provide adequate grounding and bonding. Grounding and bonding are essential for electrical safety. Ensure that all electrical equipment and systems are properly grounded and bonded to minimize the risk of electric shock. Sixthly, install overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Install overcurrent protection devices of the correct size and type to protect your electrical system. Seventhly, inspect and test your work. After completing the electrical installation, inspect your work carefully to ensure that it meets all code requirements. Test the system to verify that it is operating safely and correctly. Finally, document your work. Keep a record of all electrical work you perform, including permits, inspections, and test results. This documentation can be helpful for future maintenance and troubleshooting. By following these steps, you can ensure that your electrical installations comply with local electrical codes and regulations, reducing the risk of electrical hazards and ensuring the safety of people and property. Always remember that electrical work can be dangerous. If you are not qualified to perform electrical work safely, it is best to hire a licensed electrician to do the job. Safety should always be your top priority when working with electricity. This information is for educational purposes only and should not be considered a substitute for professional advice from a qualified electrician or electrical engineer.